All right. Let's go ahead and slowly get started. We left off last time describing waves. We went through some oscillations. Now we're talking about wave motion, and we just left off describing properties of waves. This pen works. So, just in general, we have a wave. This is considered one wavelength from here to here, is because any other point after this, if it kept going, will just repeat the same thing over and over again. So that's one wavelength. That's also one period of oscillation, the time it takes to go from here to here. All right, so one wavelength, and also the time is one period of oscillation. Now, these things will often be moving. They're things that transfer energy from one place to another. So in general, you can find the velocity of a wave by knowing some features about it already. So if you already know the wavelength, you know pretty much the size of it. And also if you know the frequency. Frequency was 1 over the period of oscillation. So it's the frequency is like how many oscillations, how many cycles happen in 1 second. So we're able to use these two things that we know. We know the wave's this big, and it occurs this rapidly, this often, or this frequent. We're able to find the velocity of a wave. That's just in general. Velocity of the wave is the wavelength times the frequency. Ooh. Did a whole bunch. Okay, so and I also have a thing up there. Also includes the amplitude. Amplitude is just the height of a wave. Amplitude is the same, positive and negative. Just the size of it. Now, when we're looking at waves, they can travel through different mediums. There's one core thing we could start with is looking at waves through a string. If we look at how a wave has to travel through a string, now there's this is the math version. It doesn't have to go through anything. There's no material actually moving. This is just an idea brought forward by math. But now we think of the real world. Waves have to travel through stuff. So if we're looking at waves that travel through a string, like a really simple, fine string, we now have to consider, what is the string made out of? How much mass is in the string? The real world objects have mass. And also, how much tension is in the string before you find that wave? So not quite a string. This is like a rubber, rubber cord. I could give a little pulse and find the speed of that wave that first traveled down. Let me do a little. See, that wave that traveled that way, it went a lot slower when there was less tension. If I go way over here, it went a lot quicker. So depends on what the string's made out of, how much tension there is. So that leads us to this equation, or this form of the velocity of a wave through a string. That's related to the force of tension, I'm going to write like this. I'm not going to write T since we've had too many capital T's lately. That's the force of tension over, this is a mu. It's a Greek letter mu. I'm going to write it real fancy on the board. So it looks more officially like that. That is the linear density of a string. So think of regular density. This is rho. It is mass per volume. The linear density right here is mass per length. Same thing. It's a density, but that's 3 dimensions over there. This is 2 dimensions. So this is just mass over length. I'll add that on the slide also. So let's see. Mass per length. That's the linear density of the thing. And that's tension on the numerator. Okay, so waves that travel through materials have to actually move through the stuff. Let's see, what's my next slide before I change the subject? So, waves that travel through strings, they might have some tension. Well, waves that travel through air, slightly different. There's, molecules hitting each other. Then sound or other types of waves can move through materials. So, a sound wave, we'll get to sound proper in a minute. But sound can travel through materials as well, and it depends on what the material is made out of. Very similar to this. I don't have an actual section on this, so I don't want to bring it up right now. So I have this aluminum bar here that I can produce some sound waves. The sound wave will be, there'll be 2 of them. There'll be 2 types of sound waves being produced from this thing. There'll be a low frequency one that sounds really low pitch. There'll be a high pitch one. The low pitch one is from the bar shaking like this. That'll be a transverse wave. The high pitch frequency will be from the waves traveling longitudinally through the material. And similar to this, not exactly, this is for strings. Similar to that, since there's like a material, you think of it as a high tension, the waves will travel a lot quicker. And that's why we get a very high pitch sound from this. No, it's going to be kind of loud. Right here. Okay, so here's a low pitch one and a high pitch one. That was because the waves were once traveling by a transverse wave, the rod just sort of wiggling back and forth. The high pitch one, the material is traveling back and forth inside of the material. So, very similar concept to how, to how the materials put together determines how the waves will travel through it. Let me see, I gotta get this set up again. Like that. Okay. There we go. Okay. So, waves can interfere with one another. So for some instances, a wave might travel in a way that will cross over another wave. Get rid of this. So one type of interference is called constructive interference. Let me draw, well, actually I'm going to draw it on here anyway. So let me go on the slide. So let's say I send a wave pulse. You saw with this rubber cord, I just snapped my wrist, and a wave went down in one direction. So if I have a wave pulse on a string, and it's traveling to the right, and let's say I have another wave pulse that's traveling to the left, when they meet in the middle, since they're both on top of this axis, they're both oriented upwards, they're going to add to each other. They're going to create one wave that is double in height, or these two amplitudes added together. So it'll be momentarily a really tall wave, but then the two will just pass straight through each other and keep going. I started in the middle. Had it crunched up in the end. This is called constructive interference, when the two waves will add to make a larger wave. Similarly, there's also destructive interference. The same type of concept, but if one wave is sort of inverted or upside down, I could draw this one better. So if one wave is traveling to the right and it's upwards, and one wave is traveling to the left and it is inverted, it's upside down, right when they cross, let's say they're the same size, they're exactly the same size, for that brief moment right when they cross each other, they will destructively interfere, giving what appears like no wave. They've reduced each other's size momentarily as they sort of pass through one another. But then they just keep moving through. They keep moving through each other. So then that downward facing one just moves through. That upward facing one moves through that way. Where did I put it? Back here. I have like a real physical example of this. Let me bring it out. So we have a thing with some beads with a wave pattern on it. And I'm going to add another wave pattern to it. You see when I put it all in, it's going to be the exact same position. So I'm pretty much adding another wave on top of this one. And also note the green line is flat at the bottom. Right? Let's see. As I sort of add these two waves together, they're going to constructively interfere with the wave pattern, then when it's all the way in, right about there. Now you see that red line, that original line, is now doubled in height. The green line is just showing you what has been added to it. If I go, off phase with one another, that's right there is destructive interference. I could also do it with, a slightly different size wave. That's not. It's clear to see what's happening. Something that's much smaller. So it's the same. Go like. Where's a good spot? It's the same overall, but you see there are multiple waves stacked on top of each other that are constructively interfering in different ways. Sounds a lot more. Sounds more like what you see in an actual sound wave. Just put back here. Okay. So waves can also reflect off of objects. Sound wave, light wave, waves on a string, they can reflect. How do they reflect? Waves on a string, that's one of our simplest real world examples. A wave on a string reflects depending on how it's attached to something. So how is it attached to a surface? We're going to assume this is the string again. So attached but able to slide. So I'm going to try my best to draw this out. So I don't have that example. I don't have that demo set up right now. So I'm going to try to draw this the best I can. We have, let's say we send a wave pulse upright, and on the end of the string, it's like on a ring. It's attached to a ring that is going around a pole. And the wave is traveling that way. So as the wave, we know, will travel down the string and it hits that surface. As it hits the surface, you imagine that ring that's on the pole, it's just going to slide up and then back down. And what we'll see is that the wave is reflected and it stays upright. So it will reflect and stay upright. If we have a string that is attached, permanently, it's to a fixed point, more like the demo I have up front. If I have a string and I send a wave down, and it's attached to a fixed point, it'll travel down the string, hit the surface, and it will reflect, but it'll do something a little odd. It will invert. It'll turn upside down as it starts to come backwards. There's the wall. So let's see if I can do that. So I have a similar to a string that is attached to a fixed point over there. And I'm going to try to make a wave that is upright. Let's see. ready? 3, 2, 1. Let's see, maybe I need to go. I can't really get it. Let's see. Kind of. I should have practiced this one first. Okay. So the wave will reflect upside down. So we have this potential of a wave. If I send a couple pulses, the string can create waves that will interfere with itself. And there is a section on standing waves that I don't know if we'll have a time to get through this semester, but that's also a property of sound waves and other types of waves. But here we have some fundamental parts of how waves might move. That leads us really well into sound. Okay. All right. So for this chapter on sound, I'm kind of like really chopping it up, getting to the parts that I think are most important, although I think this is one of the more interesting things. I wish we could have gotten here a little sooner. So the speed of sound, we're going to say in air. For most of our demos and activities, the speed of sound in air is similar to what we've looked at with that simple case. We consider that string the simple case. It's just a wave moving through a small piece of fabric that's only moving in one direction. When we talk about a wave moving through air, that's a lot more complex. How does sound actually propagate through this room? It's hard to actually picture it in your mind. You picture there's like this cone of sound waves coming out of my mouth, sort of emanating, flowing towards you guys. All of these, thousands of molecules are just moving back and forth, propelling these, sound waves, this energy outwards. Also, similar to how, in a string, a sound wave depends on how much, similar in a string, the velocity of the wave depends on how much tension there is. A sound wave through air relies on how warm the room is, or how much motion is already in the molecules in the environment. So the speed of sound, I'm going to go like this. This is like a really general one that we might not need. This is related to me using that aluminum bar right here. The B is the bulk modulus that's related to like a material's density and pressure. That one I don't expect we'll be using that often. Since we're just going to be talking about air most of the time, I'm going to use this form right here. T for temperature. I'll just spell the whole thing out. So temperature over 273 Kelvin. Yeah.
Does this mean sound travels faster in warmer environments?
They do. So, yes.
Temperature in degrees Celsius?
Temperature is also in Kelvin.
Oh, okay.
Yes. So this is let me make this K. Right. That's actually a problem with people doing track on a cold morning. Starting gun goes off, and you hear it at different times. That's also how the sound waves travel. It's going to hit the person in front if you're doing that. When they're lined up at an angle. It's going to hit the person in front before it reaches the person in back. So that's why I think most people are using the sort of light display. You actually have to look at, because light waves travel way faster than sound. So everyone pretty much can see the light waves at the same time. Sound waves, it's like this rolling hill that passes by everyone. Yeah, and it depends on the temperature of the environment. This, I should say, this right here is at 0 degrees Celsius. So they've sort of measured the sound wave, the velocity of sound at 0 degrees Celsius, and that's why you see 331 right there of air. It's just not me, throwing random values at you guys.
Professor?
Yeah.
Have they recorded the speed of sound at temperature like 4 Kelvin that's really close to like absolute zero, like liquid helium, for example? Just out of curiosity, I asked.
I'm not sure. I think if something is that cold, it would be hard for it. It'd be like a sound moving through a material. I expect it would probably be fairly slow. Because again, right, it's the molecules actually hitting each other. And if there's not that much energy, the molecules themselves don't bump into each other that often. So it's interesting. I'll have to look it up. Yeah.
So like in space, would that mean that there's like no sound?
In space, there is no sound, right? One, it's because there's no air. There's no molecules to bump into each other to carry the vibrations to your ears. That's the main thing why there's no sound in space. Also, extremely cold. Yeah. So let me actually go back 1 second to the talking about sound going through materials. That's also a reason that you may have noticed it, you may not have, but sound actually moves quicker if you're underwater. If you've ever heard something underwater, sound moves incredibly fast because there's already water molecules right next to each other. That's why a lot of things in the sea develop this echolocation, because they can have this sound wave carry for hundreds of miles in the water. That was a little tidbit. Now we're on to the Doppler effect. The Doppler effect is something related to how the sound waves may bunch up when something is moving. So when a source of a sound is in motion, then the sound waves, the frequency heard may not be what actually is being produced. So there's a little picture explaining this. So I had up that vision of the sound waves going out, equal velocity in all directions, right? So that's this car that's stationary. Sound's just moving in all directions equally. But if the car itself is moving in one direction, you can see the sound waves might bunch up on one side. And on the other side, they're going to stretch out a bit. And this sort of, bunching up and stretching out, that changes how frequent you hear the sound waves, reaching you. This changes the pitch of the sound. So that's why, you hear train coming, it's really high pitched, and then when it goes past you, now it's going away from you, the train is low pitch. So I have this next animation. I don't want to leave it up because it looks like I'm hypnotizing you. So as the object moves in one direction, the things bunch up. And they are sort of more spaced out on the other side. So it's all related to how the object is moving. Is the object moving, or maybe the person is moving? So, what if, ignore the bottom picture, look at the, stationary car up top. What if, the sound is equal in all directions, but a person, or maybe you're in a car that's moving really fast towards the sound? That is also going to produce the Doppler effect, because you are moving and the waves are hitting you faster. So there are a few ways that we can arrange this problem. So when there's a stationary source and a moving observer, so the car is staying still, someone in another car coming past, you hear the horn, really high pitch as you're coming in. And as you pass the car, the horn might be low pitch. So let's see. Let me say first, I'm going to say moving towards. So the frequency heard by the observer heard from the observer is going to be equal to the frequency that is actually being produced, the frequency from the source, all times this ratio here. V plus V naught over V. So V, let's see. V is the speed of the wave. And V sub O is speed of the observer, velocity of the observer. So pretty much when you're moving towards, when the observer is moving towards the sound, so I'm like riding my bike really fast towards a car that's honking, I'm hearing something that is higher pitched. This observer frequency right here is going to be a larger number. It's going to be a higher pitch. When I'm moving away, let's do this. So for moving away, that sort of thing on the numerator is this instead. Now, if you're a stationary observer, you're at a train track crossing, you're waiting for the train to pass. The source is the thing making the sound, so it's approaching you. So it's moving towards. We have this relationship. The variables mean the same thing. So now V sub s, that's the velocity that the source is moving. How fast is that train going? How fast is it approaching you? So it's moving towards you in this version. If it's moving away, then the thing you're going to change is instead it's just going to be V plus Vs on the bottom. And V, that's the speed of the wave. And since people got irritated having to use two different versions of this, they came up with a general form. So they just took the two and they spliced them together. So this is for something moving towards you. You have to remember to flip the things I have over on the right if something is moving away. All right. I have an example here. The Doppler effect. It is a ball. You can't hear this. You might need to get some hearing check. Does anyone can't, like you're not able to hear that? Okay. All right, let's go like this. And it stopped. You guys don't hear it? No. You hear it changing. But it's still doing the same thing. The sound is just being really bunched up when it's heading towards you, and it's stretching out when it's moving away from you. So when it's up here, it's a low pitch that you hear. Okay.
Is sound being directed towards the center? Like, I don't know, I'm kind of thinking about centripetal force, but I know sound isn't a force, but does that have anything to do with that?
It's not really, connected to the circular motion of the ball. Not really.
Okay.
You think of it as like I'm just like tapping water in a circle. I'm just creating ripples in a circle, and they're spreading out in different directions. Okay, let's do an example of the Doppler effect. Real brief one. So I have a train that's moving at 40 meters per second, and it has a horn that produces a frequency of 500 hertz. And a stationary observer is hearing this train approach them. But what is the frequency that the observer hears? I should also say that the temperature at that moment is, the air temperature is 24 degrees Celsius. So, first, we need to see how fast does the speed of, what's the speed of sound in air at that temperature? That's the first thing we need to figure out. So how fast does the sound move? We need to know the velocity of the waves. All right, so velocity of a sound wave. That was just this thing. T over 273 Kelvin. Was it's 24? I have to convert to Kelvin. So 24 plus 273, that's 297. So the velocity of a sound wave at that temperature is 345 meters per second. All right, so we found the velocity of the waves. Now I can use pretty much this, just like the general form of the Doppler effect. So the frequency heard by the observer is equal to the frequency produced by the source. Now is that big fraction? That's the velocity of the wave, velocity of the observer. This is velocity of the wave minus velocity of the source. And I don't have to switch anything because the train is moving towards the observer. The train was moving away from the observer, and I'd have to switch the signs on these things. All right, so we have the original frequency was 500 hertz. And the observer is stationary, so that's 0. The speed of the wave, 345. And we have the speed of the wave minus how fast the train is moving. So we get something that looks like this. We have the frequency heard by the observer is a little bit larger, 566 hertz. So that's a completely different tone. It's a higher pitched tone. It's a bigger frequency. Similar to that ball, it's approaching you, sound waves get bunched up, it's more frequent. They hit you more frequently. Yeah?
Can you explain what you meant about switching the signs for if the train was going away from?
Right, so remember I had on the right side, if it's moving away from you, instead it would be V.
So you change it for the general form too?
Right, yes.
Oh, okay.
Yeah, so let me put it on the board. So the general form is plus and then minus. So that's towards you. Did I do that right? Yeah, that's towards you. You would flip that and then that if it's moving away from you. That would be, I'll just do it again. That is away. This is towards.
So like if you have a hertz that is lower than the actual source, it's most likely that it's moving away from you?
Yes, and that's the the easy thing to help you. Like a higher frequency means a higher pitch. I always just think back to that picture. The waves are hitting me more frequently. It's a bigger frequency. If it's moving away, I'm getting hit by the waves less frequently. Okay. All right. Yeah. Shock waves. So we've looked at the Doppler effect. We've looked at sound waves, the things that move. But sometimes things might move faster than sound. What they're going to do is they're going to bunch up all of the sound waves together. Main example is like a fighter jet. You're seeing it's breaking the sound barrier. So what it's doing, it's moving faster than sound. So you see these small dots right here, that's observer 1 and observer 2. Why you hear a big boom, like out of nowhere, because all of those sound waves hit you at the same time. Yeah.
So let's say the jet was like stopped in air with the sound waves like catch up with it.
Like if it slows down?
Yeah.
Yeah, they just like pass it and go forward. Yeah. No, yeah, exactly. So,
would that be dangerous? Because wouldn't the sounds have a chance to break that window that's there?
Yeah. Mainly it's like the air molecules hitting the window. Right. So the jet would be moving so fast it can't hear its own sound that it's producing. Okay, so that's one form. Another form of like a shock wave is from a explosion of some kind. So if you guys can look real closely, around the edge is like this bubble that's created. And that's the pressure of the air that's being compressed together. And why we actually see a bubble is because the light refracts differently through this highly compressed air. Also, the sound waves temporarily have been broken from a small whatever was exploding. Yeah. What else? I think I only have a couple more things. Resonance. So objects that oscillate, all of these things that might move back and forth, create this wave motion. All of these things have the ability to make other things also oscillate. But they have to be very, 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 very similar. So this forced vibration is called resonance. And right here, I could force vibration. I could do some resonance from this tone box right here. It'll produce a sound. This is, I think it's an A. Not sure. I think it's an A. This one over here is also an A. They're the same. Make sure they're completely stopped. Since they're both exactly the same, I can create a resonance from this thing right here to produce sound waves. Since it matches identically with this one, very similar object, it will force a vibration in the metal, in the material. I'm gonna try my best. You guys probably won't be able to hear. I'll put it on a table. Maybe that'll work. It's that one over there. I can do it that way too. So this is the resonant frequency of these objects. Energy is transferred from one object to another object. It's making it make sound. Even though I didn't even hit this one. There's also what's called a beat frequency. We're not going to be able to get to. It's how closely the sounds are together. You hear them like fade in and out. That's something like piano tuners use to help them out. So that is resonance. There's also destructive resonance. Maybe you force an oscillation that's too large. I just made a little sound. What if I do something that forces an oscillation that is maybe dangerous? So many of these objects have a very specific resonant frequency. This one is very easy to tell. I'm just going to assume it's an A. So that means this one is also an A note. Are there any music people in here? What is the frequency of an A? It is? Are these A? Yeah. Okay. Awesome. 440 hertz. So that means there's, that many oscillations per second. So if you try to force something that maybe it doesn't want to oscillate, you could end up breaking things. You could use the sound of your own voice to shatter a glass. It's not, fake. You could actually do that. They have this one right here next to a speaker, but up top, that's actually what's happening. So you find the resonant frequency of the glass. Maybe you run through some pitches with your voice. And you hear right when it starts to vibrate a little bit. That's the resonant frequency. So you just need to produce enough of that resonant frequency. You see the glass starts to violently shake. That will break it. So there are other, even more violent, destructive resonant frequencies. You build a bridge incorrectly over a pass that gets a lot of wind, and a lot of wind is the exact resonant frequency of the bridge. It will build more and more and more destructive energy. You guys want to drive on that? I think it was just deemed unsafe, so they tore it down. That's a separate video that they attached to it. This is in Tacoma, Washington, and it's just the resonant frequency of the wind constantly pushing at just the right amount. Other destructive resonant frequencies are in like earthquakes. We have an earthquake-proof building on the left. Here's just a normal building on the right. Let me get one more thing out. So, similar to the buildings, here, every object has a specific resonant frequency. All the skyscrapers, they do not agree with earthquakes. When the earth moves, the earth might happen to move at just the right resonant frequency. It takes a very low resonant frequency to get something really tall to start to resonate. So I'm going to simulate an earthquake. The earth is just moving back and forth, just a little bit. See, it's only the tallest is resonating more and more. If I add more energy, then we can get to maybe get that middle buildings to start to resonate. So very slow, just a little bit. There we go. And it has to be a very specific, different resonant frequency to get the smallest buildings to start to collapse or act dangerously. Right. So, buildings need to be earthquake proof. Let's see. I think the last thing I have is, you guys ever been on a trampoline and with like another person on it, and it will like bounce you up higher than normal? What they call it, double bounce. So that is people creating a resonant frequency. You're both jumping. One person adds the just the right amount of force, right frequency, to increase the the motion. We have this right here. Let's see. This might not. Let me just play it on my other screen.